Go ahead and start the recording.
Saturday.
Yes. Okay, everybody. So listen up. So Saturday is when we have our test. Okay. This test is going to cover primarily, okay, review things. So the specific things to watch for the review part of the test are going to be function basics. Okay. The other big important thing would be some inequalities. Okay. I will not throw on there trigonometry questions. Okay. Even though it's part of review, you're going to see enough trigonometry throughout the year as we do it. Okay. Or rather, I guess how the trigonometry will appear on the test this coming Saturday will be in limit questions. Okay. So I'll ask you for like the limit of the sine as x approaches pi over 2, and you just have to tell me what the answer is for that, okay? Using whatever methods I tell you to use, okay? So, but from this review we did, the specific, okay, review things would be function basics and inequalities, okay? Then, after that, the thing we're going to look at is limits, okay? And what we're going to do specifically with limits is we're going to look at them graphically. Okay. Next one we're going to look at is them, what's the word I'm looking for? Numerically. And the final way is analytically.
Will we have a review day for the test?
We have a review day.
Or like something like
I mean,
class?
if you have questions before the test, I want to see something done, I might maybe spend like 10 minutes at the end of class on Thursday going over that. Also, too, we could also, besides that Thursday, too, you could always have an opportunity to meet me or a consultation. And if you let me know, I will make myself available on Friday if I'm here. Remember, things could change at a moment's notice for me. So,
Oh, that's right.
I could just drop everything, you know. I could get the call right now, in which case, bye. There are emergency plans if that happens. Actually, having it happen on Friday would be a good thing because class the next day would be a test anyway, and so you're not missing out on anything. It would just be someone coming in here and watching you guys take a test. It's not too bad. Otherwise, I believe this class, Mr. Johns will cover one of the classes. I can't remember which one it is specifically. And then like I think Mr. Broadus covers another one, and Mr. Keene might cover the third, or Dr. McRae or something like that. Okay. Yeah. Unfortunately, a lot of math teachers were all teaching Saturday, so no fun there. All right, but these are kind of the three things to expect. Okay. So far we've covered everything up here except for limits analytically. Which we'll talk about today. But first, let's go over any questions anybody had on the homework from Monday. Okay. 28.
Yeah.
Okay, 28. Oh, I love this picture. Okay. 28. Now I'm going to reproduce. Okay. This picture as best I can here. Okay. All right. And so we've got. There's a hole there. The point's defined right there. -4. We've got.
Ooh, I missed
Point
one
right
actually.
here. That's -2 right there. Hole there. Comes up here at 4. The spike here is at 3, etc. So there we have it. Okay. And so we want to know for what values, okay, for what values of c for which the limit exists. Basically, it's a little bit easier to say where does the limit not exist on this thing. Okay, so, all right. So, Well, there's no, basically, guys, it's not asking for, there's no specific C, it's just asking, essentially, where does a limit exist on this thing, okay? So, everyone has already identified 0 as being one location, right? Why is that the case? We have a large jump there, so a limit doesn't exist there, so no limit at x equals 0. Alright, any other locations?
2.
At 2 or, that's a negative 2.
Negative 2.
At negative 2. This location right here is suspect. Now, here's the problem with this location right here. Okay? Technically speaking, remember, it depends on how you want to look at things when it comes to how you want to handle limits. By some definitions, people would say, there is a limit there. It's at negative infinity. Because that's where the left-hand side and the right-hand side go to, right? They both agree on negative infinity, right?
Is that
So,
wrong?
that would be the limit. It's technically not wrong to say that, but at the same time you could come through and say, well, wait a minute, negative infinity is not really a number. Those things just keep going down, 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 and they never meet each other. So it's a little hard to say where the left hand and the right hand side actually agree, okay? So kind of from that point of view, we would say there's no limit there, okay? So kind of keep that in mind when you're doing these things. Unfortunately, I cannot remember this off the top of my head. I'm going to go look it up right after class. Which is the correct AP answer to this question, okay? I want to say that the answer is that there is no limit there, okay?
Really?
Because if you go to infinity, regardless of whether you agree with each other going to infinity,
It's terrible.
you're still going to infinity, and it's terrible. Exactly. Doesn't work.
Are you taking infinity right now?
Huh?
Are you going to take it if we put negative infinity?
If you put negative infinity, I'll take it, yeah. Not the end of the world if you put negative infinity there, that the limit does exist there, okay? I would accept that for right now. But I'm going to tell you, generally speaking, I believe the correct answer here, or the answer that we want, is that it doesn't exist.
So are you going to change it, or you always going to take it?
I'm sorry?
Are you gonna change a rule, like on us? So you, once you look it up, are you gonna?
Yeah, I'm going to look it up and tell you the correct answer I want there, okay? I will look that up. But I'm saying right now, I believe the answer is no limit there, okay? Yes?
What if there was no point at -2, -2?
Oh, that
Would
point there?
Would that change?
Nope.
Okay.
That point does not change anything.
Okay.
It's the dip there that goes down to infinity is the problem.
Okay.
Okay.
Wait, wouldn't that point be the actual limit?
No, that's where the function is defined is at that point. So if I were to ask a different question, is the function defined everywhere? The answer is absolutely yes. Okay? Because it's defined right here. There's a skip, but they put the point down there -4, so it works. There's this drop off where it's asymptotic and seems to go down to negative infinity there, but they define a point at 2, or -2s are okay. That's just a skip, and it does something weird there, but the limit agrees and it's continuous throughout that weirdness. So it's okay. So basically the only one here is that point there. And actually, no, I should have done it just at the beginning, is just look at the book, what they say. Okay, the book's answer for this business right here is that there is no limit there, again, for the reason I gave you, because it goes to negative infinity. Okay? And even though left and right agree, since negative infinity is not a number, we can say there's no limit there. Alright? Everyone got that? So go with that definition. Alright? Everyone got that? So basically, for this thing, the limit exists everywhere for all C except C equals -2 and 0. Okay? The rest of the locations are fine for the limit. Got it?
So the answer wouldn't be at -4 and 3. That's not.
Oh, I see. So you're actually using every single dot as being the location C? Is that how you read that?
Yeah, I mean, I wrote that my answer was -4, was f of -4 and f of 3 are where the limits exist.
Right. Well, they do exist at -4 and 3.
But they also exist
Everywhere else,
except for.
those 2 locations. I think the problem here is just we're reading this problem differently.
Okay.
You're reading it as there are 4 locations specifically marked on the graph,
Yeah.
and so you're saying the limit exists at 2 of those locations, the other 2 it doesn't. I read it as being basically for what values, any value is C basically. C could be anything, what C's work for this thing.
Okay.
And the only 2 that don't work are those 2
Okay.
values.
Do you accept either? Or are you supposed to do it?
It's a little ambiguous in this case. If I were writing the question, I would write it clearer than this. Okay? If you accept, because I can see how you can see it with the C thing. So you're fine. Don't worry about it.
Okay.
That's fine. Okay.
That's fine.
Okay. All right. Any other questions about the homework from last night? Pretty straightforward, right? Yeah, limits aren't that bad. They can get weird. This is about as weird as it will get. There are some other situations where they get weird, but that's not. But they're not that bad. Okay. If there's no other questions, let's pass the homework forward. I said I'd start collecting the homework, and I meant it.
There you go.
Can't find it?
I did last night.
Yeah, find it, bring it to me later. As long as I get it before the end of the day,
Ah,
I will accept it. If I get it. Okay. You want us to do your homework.
What?
You definitely want to do your homework, Sam.
Yeah.
Okay.
Well, I was in, I switched and that's.
Right, and then switch. So, alright, that's true. So I'll give you, you're okay then. Alright. Alright. Okay. We're going to move on. Okay. And what we're going to talk about today is how to handle limits analytically. Okay. So, what I mean by analytically is we're to calculate a limit without using a graph or doing things numerically. We're just going to calculate what the limit is. Okay. Okay. And really, when it comes down to it, okay, pretty much the easiest way to do this is by a method known called direct substitution. Essentially, evaluate the function at the point in question, and 9 times out of 10, that's your limit. Okay. So for most cases, okay, when I do the limit as x approaches a of f of x, it's equal to f of a. That is, the function evaluated at the point in which we're going to the limit is the limit's answer. Okay, that's the case of the vast majority of functions. Any function that this happens to, we say it's continuous at a. Okay. Okay, so if you remember before, we've seen the term continuous before. You probably learned in pre-cal something like that you could draw the picture without the pen leaving the page. It's a continuous function. You might have even heard some better versions of something like that, like it has no holes in it, or skips or asymptotes and things. We're beginning to build up a proper definition of what it means to be continuous. Okay, continuous literally. In the case, basically, a function is always continuous if one of 3 things hold. 1, the function exists everywhere. 2, the limit exists everywhere. And 3, the limit at a of a function is equal to f of a. That is, the limit and the function agree everywhere, if you will. Okay? I'm going to write those down in a second. But this is how you find the limits analytically in most cases. Okay. Any questions so far about this right here? Pretty straightforward, right?
And you should hear me repeat those three things.
Yeah, I'm going to repeat those three things. I'll actually write them up here in a second, okay? But let's take a look at a few cases of analytical limits, okay? Some examples. Okay. Alright, so my first example, we'll keep it easy. We'll do the limit as x goes to 2 of x squared minus 3. Okay? The rule is, you evaluate the limit. Okay? At the point, that's your answer. So if I stick 2 in this thing, what do I get?
1.
1. So 1 is my limit. Okay? Easy as that. Pretty straightforward, right? Okay? Let's look at another example. Let's do the limit as x goes to 4 of 1 over x squared minus 16. If I plug 4 into that, do I get a limit? No. This would be undefined there, okay? And it's classically undefined. 1 over 0, essentially, okay? So this here would just be no limit, okay? Again, easy enough to work out, okay? I keep doing examples like this all day long. Thing is, they're not that interesting, okay? Here's where they start to get interesting, okay? And this is one where the majority of cases rule starts to not really work out, okay? Something like this one here. Limit as x goes to 5 of x squared minus 25 over x minus 5 equals what? 0 over 0, right? If I plug 5 into there immediately, I get 0 over 0, okay? This is a problem, okay? Okay, why is that a problem? What does 0 over 0 mean?
Indeterminate.
Undefined.
Okay, if I was simply evaluating this function at 5, undefined is the correct answer there. Limits, though, remember, a limit can't be undefined. They're either exist or they don't exist. And this is not regularly undefined either. It's 0 over 0. You said it correctly. It's what's called indeterminate. Okay? All of a sudden, we have an issue here with something like 0 over 0. 0 over 0 doesn't... Basically, 0 over 0 means, you know, we have a major problem here. Something's not right. Okay? When something's undefined, okay, that is classically undefined. What I mean by that is it's a constant over 0 or something like that. Okay? It's just undefined. There's no problem with that. It just doesn't work. 0 over 0, though, is indeterminate, which means, wait a minute, something else is going on here. Because you're never supposed to ever get this as an answer to anything. Okay? It turns out what's going on here, as some of you already realized, this thing can be reduced, right?
Yeah.
Okay, so when I get one of these indeterminate answers, I got to go through with the reduction. Basically, problem, function needs to be reduced, basically. Okay, so we reduce the function, and we know it reduces to x minus 5, x plus 5 over x minus 5. Those cancel, and then, that limit's easy, right? It should be 10. And so the limit there so 10 is the correct answer for the limit. Again, this gets into that notion of going back to continuity. We know this thing is discontinuous. It's got a hole at 5, but the limit still can exist even when there's a hole there. Okay? And in this case it does, and the answer is 10. All right. Everyone see how that works there. So, if I went back to my original definition, for most cases, okay, this is the rule here. We can start listing out exceptions, okay? Okay, and the first one is when the limit as x approaches a of f of x is indeterminate. Okay, your indeterminate forms, okay, the big three that you're going to see here are 0 over 0, plus or minus infinity over plus or minus infinity, and the last one is infinity minus infinity. Okay, these are the big three when it comes to indeterminates. All right, 0 over 0 doesn't mean anything. It's not 0. It's not undefined. It's just kind of meh. Infinity over infinity is problematic. Well, your inkling would be, oh, that should be 1, right? Problem though is, not every infinity is the same size. So, that's why we can't work out that, actually. We'd have to go through and see something else is going on there. And the same thing with infinity minus infinity. Again, it should be, your inclination would be, oh, that should be 0, but again, not every infinity is the same size. And so, all three of these are called indeterminates because through very easy methods, I can actually make them equal to whatever I want to. Okay? For example, if I want infinity over infinity to equal 5, easy way to do that would just be, say, 5 times infinity. We know that's infinity, right? So I divide both sides by infinity. That's not infinity, it's a weird looking 8 thing. Hang on. And that gives me 5 is equal to infinity over infinity, right? Hey, that was great, wasn't it? Infinity over infinity is 5. But wait a minute, shouldn't it also be 1? Also 2, I could do the same exact thing I just did here with the number 4, or the number pi, or the number negative 892. Again, it's all about, because I can do this with this and have it make sense every single time I do it, that can't be. So that means I have an indeterminate form. Okay? So, that's our first one, indeterminates. Okay? If this is the case here, okay, what that means I have to do is basically, generally speaking, when the limit of as x approaches a of f of x gives me an indeterminate form, I'll have to simplify the function. Okay? This usually means something needs to be simplified. Okay? Everyone got that? Mm-hmm. All right. And that's usually what that means there. Okay. Let's look at another exception. Okay, because there are more exceptions to than just plug and chug rule. Okay? Whoops, too far over. My next exception, okay? Example number 4 here. Let's do the limit as x goes to 2 of the square root of x minus 2. Okay? If I plugged and chugged, what would I get as an answer?
0.
0, right? So hey, 0 should be the correct answer, right?
You can have 0 in a radical.
Well, you can have 0 in a radical. Square root of 0 is 0.
Yeah,
But you can have negative in a radical, and what's going to happen if I choose something slightly less than 2? It would be negative and it would not work. So you can't do the approach from the left and the approach from right here. Okay? This one doesn't work. This actually has no limit. Okay? And that's because this is one of the exceptions. Okay? Basically, we have another exception for radicals where the limit, or the where basically where when x is equal to a, f of a equals 0. Okay.
Radicals
Where? There we go. Better. Radicals where x equals a leads to f of a being equal to 0. Okay. Okay. Now, this is not a this exception though means when you see this one, okay, what it actually means to do, you can't just assume it's no limit. You have to instead actually test using a different method. Okay. Okay. The reason why that's the case here is because, as I can see there, again, if I evaluated this function normally, I would get 0. Okay, and that seems like it should be the answer, but I know it's actually no limit. I had to figure out it was no limit by testing using a different method. Okay, I could have a radical give me a 0, okay, but actually have a valid limit. Okay, for example, let's do an easy example here. Okay, an example of something like that, what I just said here might be something like the limit as x approaches 0 of the basically of the square root of x squared. That seems kind of silly. Okay. Basically, this is actually equivalent to the absolute value of x, this function right here, okay? But notice here, this works for 0, right? If I put in 0 this, I get the answer of 0. If I put in -1, -1 squared is 1, I get 1 out, don't I? If I put in, so it actually works for negative numbers here because of the square on the inside. So this limit is actually indeed 0. But again, that's partly because of other reasons, okay? But that's an example of why you always have to test using a different method, okay? I just took it as is, and always said, oh, it goes to 0, no limit. Well, it's not necessarily true, okay? Any questions so far? Not sure I'm explaining this as clearly or succinctly as I can, okay? All good so far? Okay. Then, let's kind of doing a final thing we have as an exception, okay? Our third and final exception is going to be something known as the squeeze theorem. Am I spelling squeeze right? Probably not. No, I am. Hey, how about that? It's an important theorem with a funny name, okay? The squeeze theorem. The squeeze theorem is this notion that basically, if a function gets squeezed between two other functions, okay, and if those two other functions meet at a point, then that third function has to meet at a point as well. Essentially, kind of what that means here is if h of x, okay, is less than or equal to f of x, which is less than or equal to g of x, okay, for all, okay, x, okay, in an open interval, except on an open interval, containing containing C, except at C itself, okay, and if the limit as x approaches C of h of x is equal to the limit as x approaches C of g of x, which is equal to some number L, then no matter what, okay, the limit as x approaches C of f of x is also equal to L. So where this comes in handy, okay, you could have these really bizarre functions, okay, that technically look like they should be undefined, or have no limit at a point. But the squeeze theorem says, nope, it's squeezed between two other functions, we have an answer, okay? A classic example of a squeeze theorem problem, okay? Sorry, oh, you guys need a copy of the squeeze theorem still? Sorry.
Can you just explain?
Not
that
fair.
in layman's
No.
terms?
I'm sorry, what was that, Dave?
Can you explain that in layman's terms? Because I'm writing that down, but I have zero.
All right. I'm going to draw a picture of it here in a second, okay? I'll draw a picture and show you a function that actually uses the squeeze theorem to get our answer, okay? Give you guys a second to copy it down, okay? It's also in the book, so you can always just look at it there. It's on page 65 of the text. And remember, these notes are going to be posted on Canvas anyway, so, you know, feel like busting your hand trying to copy it down as fast as you can, you get access to it there. Okay. Okay. So, what does this exactly mean? An example of it? Okay. So, squeeze theorem example. Okay. Graphically, what this means, David, is if I've got three functions here, okay? My first function, h of x, okay, should be less than or equal to function f of x, which is less than or equal to function g of x, okay? So, g of x is the biggest of the functions, h of x is the smallest of the functions, okay? What's going to happen here is going to be g of x. It's this one in whatever color this is. Okay. Here is h of x. Okay. So we can say that's h of x. This is g of x. We're going to call this point here c. Okay. Notice here what's going to happen here is the limit. Okay. As x goes to c of g of x is going to be equal to the limit, whoops, wrong color, as x goes to c of h of x, right? Okay, we can see that happening from this picture, right? Any problems there? Well, automatically then, okay, we know f of x, its limit at c must be the same thing, okay? Regardless of, no matter what it's doing, it could be off doing something bizarre and weird. It could be going like, ah! But because of the squeeze theorem, it has to go through that point there, okay? And so the squeeze theorem says the limit as x goes to c of f of x must equal those limits right there, okay?
But what is L? Is L C?
L? Oh yeah, from the previous example?
Yeah.
From the definition, yeah, L is just a number. L could be C, L is typically a placeholder for a limit, so it just means answer, okay?
Isn't L limit g of x?
Yeah, so I could come through here and say,
That's
all these things are equal to L if you want me to, okay? In which case, f of x must also be equal to L, okay? Essentially, think of it this way. It's been, f of x we know is between these other two functions, and it's getting squeezed down to that point. That's why it's called the squeeze theorem, okay? And so, in order for this equality to remain the same, it has to go through this kind of like keyhole. And so, you know, at that point, the limit has to be the same as the other guys, okay?
Wait, so that limit is the same as g of x,
Yep.
which is the same as
H of x, yep. At that point where they're all squeezed together. And squeeze theorem. Okay? There's a classic example of a function which uses the squeeze theorem, okay? We're going to look at it right now, okay? It's going to be called, it's the limit as x goes to 0, the sine of x over x, okay? It's a squeeze theorem problem, all right? Let's take a look at this one real fast, okay? Because I know we're almost out of time, all right? So, another example, okay? The limit as x goes to 0 of the sine of x over x, okay? The answer is actually going to be 0 by the squeeze theorem, okay? Everyone got that? If I plug 0 into this thing, what would I get?
0.
I would get undefined. I get 0 over 0, right? That shouldn't be. However, actually, hang on. I've written this. Did I write this right? Oh yeah, I wrote it right. Never mind. Okay. However, by the squeeze theorem, if I actually look at this system, it obeys the squeeze theorem rules. Okay. No. Why that's the case here? If I bring up the calculator, come on. Take forever. Let's go. There it is. Okay. If I come through here and graph the sine, or graph sine of x divided by x, okay? I believe the other two ones I did on are x and negative x. Oops, no, stop that. Okay? What's it doing? Oh. Okay. Here's the sine of, I guess it goes through 1, not 0. Alright, this is not doing what I was wanting to do. Alright. We're going to have to come back. You guys are running out of time. I'm screwing this up, so. Mainly because I've screwed up this limit already. So, alright. This is actually not 0, it's 1. Okay, we'll take a look at this one later, okay? Homework is on campus for tonight. Okay, you should have all the